Welcome. This is the key for the Topic 1 quiz, but I'm going to scroll through the 10 multiple choice and go ahead and start with the Paper 2 questions and examine how you can maximize your points when taking Paper 2. So, question 11 actually started on the bottom of the last multiple choice question and continues at the top of the next page. But I've gone ahead and written the second part on here so that I have it all in one area for you. So it spanned 2 pages on your packet, and I apologize, there's not a lot I can do on the formatting. But you're told 100 centimeters cubed of ethene, C2H4, is burned in 400 centimeters cubed of oxygen, producing carbon dioxide and some liquid water. Some oxygen remains unreacted. So that's your hint that you know your limiting reactant is your C2H4. So write the equation for the complete combustion of ethene. Well, that would be C2H4. Combustion means O2. And then my two products for any hydrocarbon will be CO2 and H2O. My carbon, I need a second one here. My hydrogen, I need a 2 there for a total of 4. That brings my oxygen up to 6. So I need a 3 here to balance my equation. And that was 2 marks for the balanced equation. Then it asks, calculate the volume of CO2 produced and the oxygen remaining, which is also 2 marks, ironically. So if I start with the CO2 produced, I had 100 milliliters of this, and I had a lot of groups changing this to grams and moles. But remember, it's Avogadro's law here, his principle. These are all gases. So the water, they tell us, is liquid, so we have to do a little work with that. But I have 100 centimeters cubed of ethene, 400 centimeters cubed of oxygen, which is my excess reactant. But my 100 milliliters is going to be completely consumed. So my 100 milliliters is going to form 200 milliliters of CO2. Because when I look at my molar or volume ratio in this case, I have 2 liters of CO2 for every 1 liter of C2H4. So my CO2 produced is 200 milliliters, and that's what they wanted it as, was a volume. My second one, I have to find out how much oxygen is left. So first I have to know how much oxygen I used. So I can do it either way here. I can go ahead and use the 200 milliliters of CO2 and work backwards. If I had 200 milliliters of CO2, I can assume that I needed 3 moles of oxygen for every 2 moles of O2 or CO2. So 3 times 200 over 2 is going to be 300 milliliters of O2 that was needed. And since I started with 400 milliliters, I can now go ahead and subtract the 400 that I used, or that I had, minus the 300 that were used, and I should have 100 milliliters of O2 remaining. Number 12 says an oxide of copper was reduced in a stream of hydrogen as shown below. So I've got H2 coming in here. This is some kind of copper oxide. So I'm not sure if it's copper 1 or copper 2, so I'm going to put CuXOY. And it's going to burn off the excess hydrogen over here. And that means that basically I have a sealed system. I'm only allowing H2 in. I'm not allowing oxygen or any air into this system. It says after heating the stream of hydrogen gas, the stream of hydrogen gas was maintained until the apparatus had cooled. And so the bonus question down here says, explain why that was done. Well, because this is hot in here, and this is cooler outside. As this cools down, if you don't continue to funnel the hydrogen through here, then the pressure in here is going to drop, and you would have air along with oxygen re-entering this container. And when oxygen re-enters, some of your copper that had been recovered is going to revert back to copper oxide. So you're preventing any air or oxygen from re-entering and reacting with the copper, oxidizing the copper. And then on the next page, we're going to use this data here. So as we look at it, it says calculate the empirical formula of the oxide of copper. And this one is pretty straightforward. You have a dish that weighs 21.75 when you have the copper oxide in it and the dish. The dish itself weighs 13.80. So this is my before measurement. And so if I subtract my empty dish from my dish with the copper oxide, the 7.95 grams, that should be all copper oxide. And then I also know that my dish afterward weighed 20.15. And at that point, that should be all copper. So when I subtract these and I get 6.35 grams, that should be my mass of copper only. The other thing I need then for my empirical formula is my mass of oxygen, and if I simply subtract these two, I get 1.60, and that difference in mass has to be the oxygen that was driven out. So now I can take the 6.35 grams of copper, divide by the molar mass of 63.55, and I have 0.1 moles of copper in this from this copper oxide. The 1.6 grams of oxygen divided by 16 grams per mole means I also had 0.1 moles of oxygen. So since my molar amounts are equal, I can assume that this is CuO, or copper 2 oxide. So write an equation for the reaction that occurred. Now that I know this is CuO, and it was hydrogen being streamed over it, I can assume this is just a single replacement reaction between the hydrogen and copper, since they're both the anions or the positives, and it's leaving me the copper metal, and then H2O would be my other product. So two changes I could expect to happen in there. I should definitely see some water vapor or water droplets. With the heat, I would expect it to be vapor, but I should see some steam or droplets in there. And then the other big change is that my oxide, my solid, is going to change from whatever color it is. It's going to change color to an orange metal, which is characteristic of copper metal. Number 13, this equation was given to you at the bottom of the previous page, and you were told you have 0.6 moles of each reactant. So then it says determine the limiting reactant. I'm actually surprised you're given 2 marks for this. You could do it mathematically, but you also can look at this and it says you have equal amounts of each. The one that's going to limit you is the one that you use more quickly or more of. I use 3 moles of H2SO4 for every 2 moles. So since I use, since more H2SO4 is required, and equal volumes are present, that's enough reasoning for H2SO4 being your limiting reactant. The other way you could do it, like I said mathematically, is I could take my 0.600 moles of aluminum hydroxide and look at the ratio of 2/1 for my aluminum sulfate that's going to be produced. And I see that when I produce that, I'm sorry, it's 1/2. Maybe there was something wrong about that. So I can expect 1 mole of aluminum sulfate from every 2 moles of aluminum hydroxide. That means that's going to produce 0.3 moles of product, whereas the H2SO4, also starting with 0.600, only produces a 1:3 ratio, or 0.200 moles, which again points or supports to sulfuric acid being the limiting reactant. So calculate the mass of Al2SO4 produced. Since I've already determined that I'm limited to 0.200 moles of Al2SO4, I could simply multiply that by the molar mass of Al2SO4, which I calculated to be 342.17. So that gives me a mass of 68.4 grams. C says determine the amount in moles of excess reactant that remains. And in order to determine your excess reactant, you have to first determine how much of that reactant you did use. And I can take the 0.600 moles of H2SO4 that I was given, and I could compare that to the amount of Al2SO4 that I had to use. And I see I used 2 moles of Al2SO4 for every 3 moles of H2SO4 I used. So this would tell me that I could expect to have 0.400 moles of aluminum sulfate, Al2SO4. That's how much I should have used. And then I know I started with 0.600 moles of it, which means 0.20 moles should be remaining. The other thing I could have done is, once I realized I'm going to have 0.20 moles of product made, since this is my Al2OH3, I could use the molar ratio of 3 to 1, looking at, my molar ratio of 3 to 2, 2 to 3, I'm having some trouble here. My molar ratio is 2 to 1 of Al2SO4 to 1 mole of the product being made, Al2OH3, and that would also let me know that I'm going to use 400 moles of the other reactant, of my excess reactant, and when I subtract from the 600 I started with, it leaves me 0.200 moles. And Bronsted-Lowry acid, I'm not quite sure why questions D and E popped up with this question, but that's okay, it's good review. Remember, Bronsted-Lowry acid is an H+, not just a hydrogen, but a hydrogen ion or proton donor, whichever way you want to define it. And the last of this question, part E, says H2SO4 is a strong acid. Remember that, along with HCl and HNO3. State the name and formula of any weak acid. Well, that's any other acid, carbonic acid, phosphoric acid. What you should notice is it did ask for the name and the formula, so make sure you give both, because IB will take your point off if you simply give the formula or the name. So phosphoric, H3PO4, carbonic, H2CO3, sulfurous, H2SO3, nitrous, all of your acetic acids, ethanoic, CH3COOH. You can easily find weak acids, formulas, and names in your data booklet. Number 14 then, an organic compound A containing only carbon, hydrogen, and oxygen was analyzed. It has 54.5%, or 54.5 grams of carbon, 9.1 grams of hydrogen, and the remainder is oxygen. So if I add these up, I get 63.6, and subtract it from 100, that means my oxygen should be 36.4%, or 36.4 grams. So to determine the empirical formula, I divide each by its molar mass, and I come up with the following molar amounts. For carbon, I have 4.54. For hydrogen, I have 9.01. And for oxygen, I have 2.275. And since this is my smallest molar amount, I divide each by the 2.275. And hopefully I get whole numbers, but if I have a ratio, it's not a big deal. But I end up with 2 carbon, 4 hydrogen, and just the 1 oxygen. So that is my empirical formula. Part B, a 0.23 gram sample, so that's my little m, 0.230 gram, of A, when vaporized, had a volume of 0.0785 decimeters cubed at 95 degrees, so 95 plus 273 is a Kelvin temperature of 368, and a pressure of 102 kilopascals. They want to know the relative molecular mass. Well, given the information they've given you, you should realize you need the ideal gas law, PV equals nRT. Now you could solve for N and then use it along with the mass here to get the molar mass. Or what I'm going to do is I'm going to substitute in, and I'm going to solve for PV equals little m RT over big M. And then that means that my M should be here and my PV here. So molar mass should equal the mass of my sample times the R value times T divided by P over V. And when I plug and chug with that, I have 0.230. My R value is 8.31 since I'm using the metric values. It's the one also given in your data booklet. My Kelvin temperature is 368. My volume is in liters, which I need it to be, 0.0785. And my pressure is 102 kilopascals. And solving for that, I come up with a relative molecular mass of 87.9. I actually used 8.314, so my answer might be a little different, but it's around 87.9 grams per mole. Part C then wants to know what's the molecular formula. Well, I've got a relative molar mass of 87.9. My empirical formula was C2H4O, so that's a mass of 24 plus 4 plus 16, so a mass of roughly 44. So I can see that my molar mass is roughly two times what the empirical formula is, so my molecular formula must be double at C4H8O2. And number 15, a solution containing ammonia requires 25 centimeters cubed of 0.1 molar hydrochloric acid to reach the equivalence point of titration. So I've got NH3. And if you don't remember what ammonia is, again, if you check your data booklet, it's used commonly, or it's in a number of compounds. You should be able to find it. Ammonium, NH4 plus, is slightly different, so make sure you pay attention. I'm titrating with HCl. You can either combine these to get NH4Cl, or you could write them as separate ions, NH4 plus and Cl minus. Either one is fine for the product side. And then calculate the amount in moles of hydrochloric acid and ammonia that react. Well, at 0.25 centimeters cubed, or 0.025 liters of HCl, times 0.100 moles per liter. So when I multiply that, I'm going to get 2.5 times 10 to the minus third moles of my HCl. And because my HCl and NH3 simply combine in a 1-to-1 ratio, this is also equal to my moles of NH3. So then calculate the mass of ammonia in the solution. Since I know my molar amount is 2.5 times 10 to the minus third, I could take that times the molar mass of ammonia. Nitrogen and hydrogen is going to be 17.04 grams per mole, and I can expect a mass of just 0.0426 grams.